Bismillahirrahmanirrahim. In this video we are going to continue from where we left last time. So we started with the concept of transactions, and we said that a transaction is a sequence of certain queries, maybe read, write and update, that are grouped together as a single unit, which means that they either are going to be performed all in one or nothing at all. And we looked at certain problems when we are talking about different transactions executing at simultaneously, and we looked at three problems: the lost update, the dirty read and the incorrect summary problem. So in this lecture we are going to look at certain examples to see where the problem lies and how to identify if there is a problem or not. And in the next lecture we are going to look at how to remove such a problem. So in this case, in this video we are going to look at the schedules of transactions. So when transactions are executing concurrently in an interleaved fashion, so interleaved means that they are executing simultaneously. Therefore a part of the first transaction may have executed, and then we move on to the second transaction and then come back to the rest of the first transaction and so on. So this is called an interleaved transaction fashion of transactions. So then the order of execution of the operations from the various transactions is known as the schedule or the history. So the way in which the transactions are going to be executed is known as the schedule of the transaction. A schedule S of n transactions T1 through Tn. So if there are n transactions, the first transaction is T1, and then T2, and then T3, so on up to n transactions, is an ordering of the operations of these transactions. So the way in which the transactions will happen, which read is coming first, which write is coming later, this is called the schedule S of those transactions. Now why is this important? Because we need to know whether the schedule itself is serializable or not. So a schedule S is serializable if for every transaction T participating in the schedule, all the operations of T are executed consecutively in the schedule. Otherwise the schedule is called non-serial. So if we have T1 executing first and then T2, then this is a schedule, and this schedule is serializable because all the operations regarding T1 will be executed first, and then we move on to the T2 and then execute all the queries in T2. So the pros of this is that it's a serial execution and it will never have a problem. It will never leave the database in an inconsistent state, and every serial execution is considered as a correct execution. However, there are certain issues with that, and one of the issues that we mentioned even last week is that if I go to the ATM machine and I want to withdraw cash, and somebody somewhere else in Pakistan is also withdrawing cash, so they are using the same table of transactions, it means that I cannot withdraw cash until that other person has finished their execution. So if there are 100 people that are trying to withdraw cash, it means one person will withdraw and the rest of the 99 people will have to wait for that person to withdraw cash. Now that's very inefficient way. Or we can look at it at another example. If I go to an online store, maybe Amazon or Daraz.pk or something like that, and I'm trying to buy something, maybe I'm trying to buy a pair of jeans and somebody else is also using that, it means I have to wait for that person to finish before I start. Now that's going to be very inconvenient if I log onto the website and I'm keeping waiting, and then just I'm in a waiting loop until that website everybody else is finished, and then now it's my turn. So that's going to be result in a long transaction and can hold the system for very long times. So normally we don't do that. We do allow transactions to be executed simultaneously. However, we need to ensure that a schedule S of n transactions is serializable if it is equivalent to some serial execution of the same n transaction. So even if my transactions are intertwined together, if I can prove that the result is as good as having one transaction after the other, then I'm good to go. And there are ways we can prove or disprove that whether the transaction is serializable or not, which we shall look at in the rest of this lecture. So here's an example. So suppose there are two users, for example, the two airline reservation agents, and both of them submit a DBMS transactions. The first user submits a transaction T1 and the second user submits another transaction T2. So there are two ways I can execute these transactions. The first one is I let T2 wait, let T1 finish the transaction. So this is a transaction. It consists of multiple statements. So there is a read, there is an update, there is a write, a read again, another update, another write. So this is the first transaction T1. That's going to be executed first, and T2 is waiting. So there's an empty, this is the timeline. So there's nothing of T2 executing here. So it will wait till T1 finishes, and then T2 will start executing its reading and updating and writing. So let's call that schedule A. So a schedule is an ordering of these statements between the transactions. Another possibility is that the T2 transaction executes first and the T1 transaction executes second. So what we need to do, so both of them are serializable, because all transactions, here we say that a schedule is serializable if for every transaction participating in the schedule, all the operations of T are executed consecutively in the schedule. So here all of T1 are executed consecutively before we go to T2, and here all of T2 is executed serially or before we go to T1. So both of these are serializable transactions. However, both of them are based on the fact that you have to finish the first transaction before you move on to the second transaction, either T1 before and T2 after, or T2 before and T1 later. So both of them are schedule A and schedule B, both of them are serializable. The next thing we need to do is we need to consider if I mix them, if I mix part of the operations of the transactions, can I prove that the result of this is going to be the same as if I had executed them independently? If I can prove that, this transaction here is equivalent to this transaction, then I don't have any problem, and then this one will also be serializable. If on the other hand I prove that this is not equal to either this or this one, then there's a problem, and it means that these are not serializable. In other words, they cannot be executed in this fashion, intertwined like this, part of T1 and then T2 and then T1 and then T2 and then again T1. That's not possible, because it's going to result in one of the three problems. Either there's going to be a lost update, there's going to be a dirty read, or an incorrect summary problem. So I need to prove either way whether they are serializable or they are not serializable. So if interleaving of operations is allowed, there will be many possible orders in which the system can execute the individual operations of the transactions. So two possible schedules are shown. We have the schedule C and schedule D. So the concept of serializability of schedules is used to identify which schedule are correct when transactions executions having interleaving of their operation in the schedules. So to understand whether they are serializable or not, which means basically to ensure whether this and or this is equivalent to one of these, what we do is that we look at the operations. So there are two kinds of operation that we are interested in: the read and the write operation. And since there are two or more transactions, what we do is we say that if two transactions are only reading the data, they do not conflict. So if both of them are just reading the data, there is no issue. They are serializable. So the order is unimportant. They don't conflict with each other. If the two transactions operate read or write on separate data items, they also don't have a conflict. So if the first transaction is reading table A and writing on table A, and the second transaction T2 is reading and writing on table B, and so we have two independent tables, table 1 and table A and B. So we say that there is no issue, we don't have any problem, and these are serializable. So there is no conflict, and the order in which they are executed is unimportant. However, if any transaction writes the data item and another reads or writes on the same data item, then the order of execution is important. So if both the transactions are reading and writing on the same table, let's say table A, then it is important how you organize the individual operations of the two transactions. So for that, to figure out whether it's going to cause a problem or not, we come up with something which is called a precedence graph. So we given a set of transactions, we draw what is called a precedence graph, and we look for certain characteristics in that graph to figure out whether this is possible or not. When I say it's possible, it means if it's possible, it means it's not going to result in any problems, and if it is not serializable or the precedence graph gives a conflict, it means that one of the three problems we discussed last time can happen, and therefore the sequence is the schedule is not serializable. It means you cannot do it in this fashion. So in order to know that a particular transaction schedule is serializable or not, we draw a precedence graph. A precedence graph is a directed graph where the nodes are the transaction names and the edges represent the order. So we are going to make a graph. The transactions are going to form the nodes, and we are going to look at whether one transaction is reading after the other is writing, or there is a write after read, or a read after write, or a write after write, and we are going to draw different edges. Remember that if the two transactions are simply reading, then we don't have an issue because nobody is updating anything. So you can have as many transactions read the data if none of them is going to write. So there is no problem with that because the data is not being edited. The schedule is said to be equivalent serial if and only if there are no cycles in the graph that we are going to draw. So to look at how this works, let's say that to draw a graph, we draw a node for each transaction in the schedule. So we are going to form different nodes where transaction T1 writes to an attribute which transaction T2 has read from. Draw a line pointing from T2 to T1. So T1 is writing after T2 has read. T2 comes before, T1 comes after. So T2 to T1, you are going to make a line with an arrow pointing from T2 towards T1 because T2 comes first, T1 comes later. T2 has read before and T1 is going to write afterwards. When transaction T1 writes to an attribute which transaction T2 has also written to, you draw a line from T2 to T1. When transaction T1 reads from an attribute to which T2 has written, draw a line from T2 to T1. So you see that there are three possibilities: read after write, write after read, and write after write. As I said before, read after read is not an issue. So let's look at an example. In fact, we have quite a few examples. So let's look at the first example and see how this works. So we have the timeline over here. So T1 through T6, these are the timelines on which the individual operations of the two transactions T1 and T2 are happening. So what we say is draw a node for each transaction in the schedule. So let's try this. So we have the first one is T1. So I'm going to write a node over here, and the second one is T2. I'm going to write a node over here. So let's look at the different operations in the transaction. The first one is read X. So nobody has had any operation on X before. The first transaction is reading data from X. So there's no issue. X is being read. Let X be a table or a variable or a row or something like that is being read by transaction T1. So it's reading on X, nobody has done anything on it, not an issue. It's going to read Y, not an issue. Then we go to this third timeline, then T1 is halted and T2 comes in between, and it's also reading X and reading Y. So we have read. So this is read after T1 has read. This is read after read. So we said as before that read after read is not a problem. So up to this place, there is no issue. The two transactions can run parallel and there is no problem. The problem comes when transaction A writes to an attribute which transaction B has read from. So transaction A, T1, writes to an attribute Y. which transaction B, which is T2, has read from. T2 has read from Y and T1 is trying to write Y. Now we have an issue. T2 is before, T1 is after. So we are going to write we are going to draw an arrow like this from T2 to T1. This shows a dependency or a precedence in the fact that this is a conflict. And then we have T2 write on Y. So the data set is the same. We said that if the data sets are different, we don't care. But in this case, the data set is the same. We are writing on Y. So we have write after write. This was write after a read. And now we have a write after a write. So this one was a problem. And this one is also a problem. So we have write after write. T1 is coming first and T2 is coming after. So from T1 towards T2, we have this. Now you can see there is a cycle. If I start from T1, I can go to T2 because of the arrow, and I can come back to T1 because of this arrow. And this is a cycle. So because there is a cycle, this means that these are not serializable. It means that this is not equivalent to T1 happening before and followed by T2, or T2 happening and then followed by T1, just as we saw over here. So we are trying to say whether we are trying to establish whether that schedule is equivalent to one of these schedules, A or B. And because we see here there is a cycle, it means that they are not equivalent. And this means that you can run into one of the problems of the lost update, the dirty update, and the incorrect summary. So one of them could happen, therefore you cannot execute it like this. So this is not possible. Let's look at another diagram over here. So in this case, what we have three transactions. So the first transaction to execute is T3. It's reading on Y and reading on Z. Now if you look here, this was just read and write, and this is read item. That's not important. This is just a pseudocode. This is not actual SQL statements. So it's just to tell you what they're doing. It's a pseudocode side of kind of thing. So the read item Y and read item Z. So T3 is reading Y and reading Z. Not a problem because it's the only one doing it so far. Then we come over here, read X and write X. Not a problem. You're writing X, but transaction T3 was operating on a different data Y and Z. Here T1 is executing on X. So different data sets, even though there is a write after a read, not an issue. You move on to this part, write Y. So there is no transaction that has operated on Y, and there is no other transaction that has operated on Z except T3 itself. So fine, up to here, no problem. Then comes the first problem, read item Z. This is a problem. Why? Because you are trying to read an item that somebody has written before. So this is a read after a write. T3 comes first, T2 comes second. So from T3 to T2, you draw this line, this line here, and it is on Z. So you put your Z over here. And then you have read item Y and write item Y. Now this one has written on Y before, so you are reading and writing on Y. So you have T3, then T1, you have this line over here, and then you are going with T2. So read Y and then write Y. Already there was a write Y over here. So you add, it's the same line. So instead of drawing another line, you just add that, this dependency is coming not only from Z but also from Y. So there are two cases which are causing this same line T3 to have a precedence over T2. So with this this is going to result in this part, and then this is going to result in this part, and this one here resulted in this x, and then read x and write x. So there is no x over here in T3, so there is no dependency. However, x was read and written in T1, so this caused a dependency or a precedence between T1 and T2. So T1 comes first, that's reading or writing on x, and T2 is doing it at a later stage. If you look at the timeline, T1 is doing an operation on x first, and then T2 is doing that operation later on. Therefore, we have a graph from T1 to T2. So it's pointing from T1 towards T2 because T1 comes first and T2 comes later. And there's a problem with x and there's a problem with y because you're dealing with these two. So that's how you come up with this. Now, if you look at this, if you start at T1, from T1 you can go to T2, but you can't go anywhere else. If you are at T2, all the arrows are pointing towards you. There's no arrow pointing away from you, so you can't go anywhere from this node. If you go to T3, you can either go to T1 and then go to T2, and then you're stuck, you cannot come back to T3. If you go from T3 to T2, that's fine. So it means that there is no cycle. So since there is no cycle, it means that these are serializable operations. What this means is having it in this fashion is equivalent to having T3, which is read y, read z, write y, write z, followed by T1, which is read x, write x, and then read y, write y, followed by T2, which is read z, read y, write y, read x, and write x. So what this graph is telling me is executing it in this fashion is equivalent to executing it in this fashion. And since in this case all the operations are done consecutively, this is serializable, and we have established that this set of this is a schedule. The way T1, T2 and T3 are operating with this timeline, this is a schedule. So this schedule is equivalent to this schedule, and this is serializable. Therefore, this is also serializable. Now the question is, how do I get at T3, T1, T2? So you can see here, the only way here is the longest one I can see here is from T3 to T1 and then from T1 to T2. That's my way. If I were to go from T3 to T2, then I cannot go from T2 to T1. I cannot cover the entire graph. The only way I can cover the entire graph without having a loop is if I start from T3, go to T1 and then T2. So this is my schedule. This is the equivalence. There are two things that I determine. The first thing is there is no cycle. It means they are serializable. This schedule is serializable. And the second thing that I determine is what should be the sequence. So I started with T3, go to T1 and then go to T2, and this is my equivalent schedule which I have written over here. So this is equivalent to this, and so this is serializable. That's how I established. Now let's move on to another example, and we see over here we have 5 different transactions. So we have let's start with the timeline again. This is a time. So this here is the time, If I have a read X, okay, I have a read X, no problem. Read Y, no problem. Read Z, no problem. V, W, W. Nobody else is in fact talking about V or W. So this means that T5 will not have any conflict with anybody else, because nobody else in the whole schedule is talking about V or W. That's why you see T5 as a separate or an isolated transaction over here that has no precedence with anybody else. So we have, in this case, now let's move on. We have a read Y and a write Y. Now you have the first problem. There's a read Y and there's a write Y. So you see that T1 and T2 have this precedence with Y. And then you move on to Z over here. So you can see that there is no issue. At least with T2 there is no issue. And then we have read here, we have a write here. Now there's a problem over here, but let's move on. Let's see if there are any other issues. We have a read Y, we have a write Y, and then a read Z and a write Z. So we have a write after we have a read after a write. So why I'm not putting read and write this as a problem, because T1 has a read Z, and then it's not going to do anything with Z at all at a later stage. So having a dependency between T1 and T3, you can write it. You see over here that there's a read Z and there is a write Z. So T1 comes first and T3 comes second. So you have this edge over here, and the dependency is on Z. Then you have read U, and nobody else is talking about U, so forget about this. There's U and U over here, so these are unimportant to us because nobody else is using U, just as these were unimportant as well because nobody else was using V and W. And then we have read Y and write Y. Now there is a read and write with T2. So T2 and T4 have problems because there is a write Y and then a read and a write Y. So you can see that T2 and T4 has problems. T2 comes first and T4 comes second, and the problem is with the value Y. And T3 has a Z, and then T4 also has a Z. So we also have a problem with T3 and T4 with Z. So this is the equivalent precedence graph. So if you can look over here, if is there any cycle, you go from T1 to T2, T4, and no, you cannot move from T4 to anywhere else. And you go from this side again, there is no issue. So this is serializable, and I can execute it in any way. I can I can have T1 and T2 and move on. But we look at this what's the schedule later. So let's move on to the fourth example, and the fourth example here is the case where we have T1, T2 and T3, and the first one is a read A and then we have a write A. So you can see there's a write after a read from T1 to T2, which is shown by this line, this pink line from T1 to T2. And then we have another one from T2 to T1, which is write after write. So we have this line, and then we have write after write, which is this, and we also have a write after write, which is shown by this. So in this case, T1 and T2 have a cycle. You can go from T1 to T2 and back to T1. So there's a cycle over here. Therefore, this is not conflict serializable. Moving on to the next example, we see we have a read A and then there's an update on A, and there's a second read A over here. So read after read, not an issue. There's an update, not an issue. But a write after a read, there is an issue. So once you have this, you are going to write a dependency between T1 and T2, which you can see over here. And then we have on B, we have a read here and a write here. Therefore, you have another dependency. There's also a write after write. So that's another problem as well. So in any case, whether you consider this or not, there is a cycle from T1 to T2 and from T2 to T1 back. Therefore, this is not conflict serializable. And a final example is we have this. So let's try to solve this. We have a read X. So in this case, is the first read, there is no conflict. We have a second read, it's a read after read, so there is no conflict. The third one, there is a write after read, so you see there is a line over here, there's an edge. And then we have a read after write, so there is an edge from T1 to T2. And then there is a write after read, so there is this edge. So from T1 you can go to T2, T3 and back to T1. There is a cycle over here. So since there is a cycle, it means that this is not serializable. So this is how we determine whether it's serializable or not. And in the next lecture, we are going to look at how to deal with the cases where they are not serializable, how to readjust the transactions so that they become serializable. So if I have something like this, I will have to break one of these edges so that it no longer makes a cycle. And how do we do that? We are going to look at it in the next lecture. So that's what about serializability and whether the transactions can happen concurrently or not. So if there are any questions from this lecture, you can ask me on the YouTube comments or in the Teams. So with that, I hope it's very clear, and that's it for today.